Alright everyone, welcome back. So today we're going to be talking about Newton's method. And Newton's method is going to help us solve a problem that comes up a lot in the study of mathematics. You may remember this problem from pre-calc and even college algebra. And that is finding the roots or the zeros of a function. Now if you remember from before, the roots of a function are precisely the points that make for which the function is equal to 0. What that means is that those are the so-called x-intercepts. So Isaac Newton developed a method for approximating the roots of a function, and this method of approximating the roots of a function utilizes some of the ideas that we have spoken about before, such as finding the tangent line and taking obviously the derivative. So just to illustrate what this problem is like, so we have a function f like this, right? Clearly f has a 0 at this point. Let's call it c. Well, if I wanted to approximate or find the value of c at that particular point, I will start by first picking a point that's close to c. Mind you, it's nice when we have a graph, but if we don't have a graph, this actually becomes much more difficult to these estimations, because clearly we will see that the x-intercept here is z. Well, anyway, let's say we pick up a point on the x-axis. Let's call it x1. That means that somewhere up here we will have f of x1, right? The output value. If we were to now take and find the tangent line at f of x1, this tangent line is going to go down like this. And that tangent line is going to have an x-intercept. Right? Let's call that x-intercept now x2. Well, x2 also has an output value on the function. Let's call it f of x2. So that's a point on the graph right here. But guess what? X2 also has a we can also find the equation of the tangent line for x2 here. So if we were to draw a tangent line, it will be something like this. Now we have a point here. Let's call it x3. So this point again has a value in our function f, namely f of x3. And again, we could find the equation of the tangent line at this particular point. And if we do this consecutively, you will notice that x of x4 now, the values are getting closer, the x values are getting closer and closer to c. So for example, f of x4, the tangent line here is going to be looking like this. And we're going to have an x-intercept right here. So we get an x1, we're getting very close to c. So what Newton's method does is do exactly this iterations. It allows us to have a method for computing these values without having a picture, and also without having to compute the tangent line at each individual step, which is actually extremely useful. Let me first give you the theorem, what the theorem says, and then we'll do one example. And I'm only going to do one example because at Lehman we do not cover Newton's method in Calculus 1 typically. This is something that you will definitely see on your Calculus lab class. So this is again Newton's, some respect to my mom, Newton's method. Alright, so first of all, let f of c be equal to 0, where f is differentiable on an open interval containing C. So the output f evaluated at C is equal to 0, meaning that C is the x-intercept. Then, to approximate C, we use the following steps. Number one, we'll make, much like I did before, we'll make an initial estimation of x1. And this x1 has to be close to C. Okay. Obviously, if we have a graph, it makes our life much easier. Then two, we will determine a new approximation by following the following rule. And that rule is x of sub n plus 1 is equal to x of n minus f of xn divided by the derivative evaluated at xn. And 3, if the distance between xn and xn plus 1 is within the so-called desired accuracy, then we let xn plus 1 serve as the final approximation. Otherwise, we return to step 2. And we calculate a new one. What this means is basically, if, for example, let's say we know that the series of the function, let's say we know that f of c is equal to 0 when c is 5, right? Let's say we do the approximation and we get, let's say xn plus 1 is equal to 8. Well, 8 is 3 full integers away from 5, so we may not want that because it's not close enough. We want this distance between c and xn plus 1 to be, let's say, less than or equal to let's say 1 over 100. We want this distance between these two numbers to actually be very small, even smaller than this. I mean, this is not that small of a number, all things considered, but we want that distance to be actually very small, so that we will have a more accurate approximation. All right, so let's see this problem in action. We're gonna find an approximation using Newton's method to find a 0 for the following function. So we will use Newton's method to approximate a 0 of the function f of x is equal to x squared plus x squared minus 2. And given is x1 is equal to 1 as the initial guess. Now remember, if you're not given a guess, then you could just pick one. Okay, you could pick a value for x of your x1 to have your initial guess. Now the formula again is, for Newton's method, is xn plus 1 is equal to xn minus f of xn divided by the derivative of xn. Okay, so what we have here, we know that x1 is equal to 1. That's our initial step. That means that x2, remember x2 is the same thing as x1 plus 1. And that's how we get to x2. So we take the previous one, which is x1, and we added one more. That is going to be equal to x1 minus f of x1 divided by the derivative evaluated at x1. I'm simply substituting xn by what came before it, which is x1, and that is actually equal to 1. And I'm going to plug in here x1, which is 1, and I'm going to plug in here also x1, which is again 1. And we're just going to do those evaluations. And that's going to give us the value of x2. So before we go there, though, let's find the derivative of f. So f of x is equal to x squared minus 2. That means that f prime of x is equal to simply 2x. So now we're ready to find x2. So x2 is equal to x1 minus f of x1. Now, if you take f of x and you plug in x1, what do you get? Well, you get x1 squared minus 2 divided by the derivative of f evaluated at x1, and that's going to be 2 times x1. Well, what is x1? x1 is just 1, so it's going to be 1 minus 1 squared minus 2 divided by 2 times 1. This is equal to 1 minus 1 squared is 1, 1 minus 2 is minus 1 divided by 2. So this is equal to minus minus is plus, so it's going to be equal to 3 over 2. Yeah, 3 over 2. Okay, so that's the value for x2. Now let's go for x3. What will the value of x3 be? Well, the value of x3 is going to be equal to the value of x2, because it's the one that came before it, minus f of x2 divided by f prime of x2. So we simply plug in here the value that came before it. So we already know what x2 is. x2 is 3 halves. So it's going to be equal to 3 over 2 minus, let me redo this. Let me write x of x2 minus x2 squared minus 2 divided by 2x to the 2. I'm just rewriting this, first rewriting the f with x2 plugged in, and then the derivative with x2 plugged in. And then we substitute the value from before, which is 3 halves. So this is going to be 3 over 2 minus 3 over 2 squared minus 2 divided by 2 times 3 over 2. Okay, so this is going to be equal to 3 over 2 minus, well, here what we have is 3 squared over 2 squared, which is 9 over 4 minus 2 divided by 3, because the 2's here cancel out. We could combine the numerator first and then divide. So I typically prefer to do that. So it's going to be 3 over 2 minus. To combine this numerator up here, we just multiply top and bottom by 4. Okay, so we're going to have negative, and then have 9 over 4 and then minus 8 over 4, then all divided by 3. This negative is from the outside, so if you want to separate it, you could put it in parentheses, so yeah, you don't get lost. And this is a terrible board use because I have so much space to my left side, but that's okay. Maybe I should just move so it could be in the middle of the screen. Alright, so we have 3 over 2 minus, and then 9 minus 8 is 1, so we have 1/4 over 3. And then by the keep change flip method, you just multiply by 1/3. That's essentially what's going to happen. So it's going to be 3/2 minus 1 over 12. And then again, we could simplify this a little bit more. We could combine them. You multiply here top and bottom by 6 over 6. And then you get 3 times 6 is 18. So it's equal to 17/12. Now you could turn all of these into fractions, and that's okay. It is easier to work with these as fractions. Like sometimes, like this will be 1.5, and then 17 over 12 will be, let's see, this will be equal to 1.41666, and it goes on. And this makes it easier to see what the pattern will be for the root. Because remember, we're still finding the root. We could do one more, so I'll do one more. So let's say we go to x4. We pick a fourth point to approximate this even closer to see what the value is. So it's going to be x3 minus f of x3 divided by the derivative at x3. So remember, that's going to be x4 equal to x3 minus x3 squared minus 2 divided by 2x3, just evaluating f at x3 and the derivative of f at x3. And finally, we just substitute the values from before. And the reason why I like it more as a fraction, they're easier to manipulate, and then at the end just turn it into a decimal. I think that's just the simpler way to do it. So it's going to be 17 over 12 minus 17 over 12 squared minus 2 over 2 times 17 over 12. All right, so it's going to be a little bit more complicated. So it's 17 over 12 minus, you could square 17 and 12, so 17 squared is going to be equal to 289, and 12 squared is 144, minus 2 divided by, this cancels as one of these, so we have 17 over 6 in the bottom. Now, what I do like to do is to combine the numerator. So I'll combine 284 with over 144 minus 2. So let's do that on the side. This is 280. Let me not use this color. So it's going to be, fine. 284 over 144 minus 2 times 144 over 144. So this is going to be equal to 284 over 144 minus 288 over 144. And then this is going to be equal to minus 4 over 144. So now we have 17 over 12 minus 144, minus 4 over 144 over 17 over 6. And you could, they're both divisible by 2, so you could do that. May even be divisible by 4, but I'm not even gonna bother. I'm just gonna do keep change flip and multiply by the reciprocal. It's gonna be 17 over 12 plus 4 over 144 times 6 over 17. So this is equal to 17 over 12 plus 24, and then 144 times 17 is 2,448. And then again, we just have to make the denominators the same. So easiest way to do that, if you don't know what to multiply 12s by, just multiply them by each other. You know, you do the multiply 17 by 2 for 48, 24 by 12, and you will get the solution. So this just boils down to now basic arithmetic. So here in the top is going to be 41,616 plus 288 divided by 12 times 24, 48, which is 29,376. So when you combine this, you get, let's see, 41904 divided by 29376. And then if you turn that into a decimal, you have that equals roughly 1.719, unless I made a mistake, 067. Hopefully I didn't make any mistakes anywhere, but I could have. In any case, you know, you will keep approximating by using Newton's method, and eventually, I think I did make a mistake though. There is a mistake somewhere. Let's see, and I think the mistake came somewhere here. This is a 17. Okay, let me do this again. Let me just check. Now 17 times 24. Well, 17 times 2448. That's 41616. 12 times 24. That's 288. 288 plus 41616 is 41909. The denominator 12 times 2448 is 29376. No, that's correct. Alright, so that's the solution. Yes. Anyway, that is how you use Newton's method. So if you were to actually we actually know what the zero of this function is, because we could find it by solving for 0. So we have x squared minus 2. When is that equal to 0? Well, that's equal to 0 when x is equal plus or minus radical 2. So that will be the solution for the problem. So that is Newton's method. It's a very quick lesson. We are not going to be tested on it, or there will not even be homework on this, but I thought it was important for you guys to see it. Okay? Thank you for your attention.